This is session 2, and we're going to cover static equilibrium. And just like to talk a little bit, so this is a brief review, but just talk a little bit about what you thought about session 1 when you were doing the work, if there were any questions. Right? So yesterday we discussed the 3 primary structures we'll be covering in the class: bars, shafts, and beams. And we discussed how we go about looking at the scaling laws for how we can adjust the amount they can support based on their geometric parameters. And so for the bars, right, we said it's the cross-sectional area. For the shafts, we said it was diameter cubed. And we said for the beams, we had the load proportional to the width, proportional to the thickness squared, and inversely proportional with length. Okay. Were there any surprises or anything that came up that you want to discuss on the assignment that you turned in? It looked like people were nailing it based on what I saw, but were there any questions, thoughts? Okay, inspirational experiences. Okay. Did anyone kind of keep track of their notes so that they could see how they did these problems later on? Yeah, okay, so you have like a running notebook. I think that's a good idea. If you have questions on a problem, as you can tell, or maybe you can't tell, I'm not really putting out the solutions, although we went through a lot of the problems yesterday, right? So you had like the algebra at least. But if you have questions on how to do something, just let me know. Yes?
I do have a quick question, actually.
Yes.
For question 9, you said the short way of doing it was assuming that the rotational power is equal to the linear power. Is that always going to be the case?
Okay. Well, so I sometimes have issue with superlatives, right? So always is a strong word, right? So you can generally, as long as they're not losses, if we assume that they're not, if energy is being conserved or power is being conserved, then yes, you could think of, from one regime or to another without having loss. Now, is it possible that you have an electrical system, for example, that then results in translation and rotation, right? That would be some type of example where, maybe I have to sum the powers then if I have a system that has linear, right? I have one motor, but it's doing both linear and rotational motion, and then, you have to look at those 2 powers coming together. In reality, you always have losses, okay? That's how it goes. That said, electric motors are very efficient, and with the appropriate transmission, we're talking, 95% plus, like 97, 98% efficiency. So, and some of these assumptions are not bad, okay. But good question. Any other thoughts? Yes.
So when you're doing like the scaling up and stuff,
Yes.
with like let's say you're trying to find like the torque of a shaft or something,
Right.
There's the original one.
Yes.
Do the units of the diameter matter? So if it gives you like the torque in Newton meters, do the units of the diameter have to be in meters?
Very good question. What do you think?
I think so. I mean, I wasn't sure because there's a question on the homework where it gave you the units in times pounds, and then the diameter was in inches.
Right.
It
Right.
worked out.
Yeah. So, right, like you're saying, right? Let's say we have a torque, new, right, and you have a torque old, right, and let's say that we have a D new, and we have a D old, right, and we're saying that goes with a third. These units are going to cancel out. So what's really important is that the new diameter and the old diameter, right, have the same units. In order for this to then be dimensionless, and for this, right, to have the same dimensions as that. So you do have, yes, can you go from Newton meters to feet pounds in the factor of 1.36 or whatever like that? Absolutely, right? If I ask you to do the, to transfer over to different units, right, to convert. But here, yeah, as long as these units are the same, that would be fine. But if someone gave you feet and, and meters, right, then you've got to convert and make sure that they line up. Does that make sense? Yeah, good question. Good question. Okay. All right, anything else? Good, let's see. I'm working on names still. We have, so Nasir? Okay. And, okay. Sharif? Yeah. And then, did Isaac? Yes, okay. All right, folks, we have a full house. Okay, excellent. Yes, and we also said that the supportable loads, they're going to be different than displacements, and we'll talk more about displacements in the future for sure. Now, today we're going to cover or review equilibrium, and some of this is going to seem very familiar, and then I hope that there'll be a few things that we discuss that might be nuances that you hadn't maybe placed prior. Okay. To start, we have Newton's 3 laws. Okay. And so you can read them here. You have the first, which says the body remains at rest or in motion at a constant speed in a straight line unless acted upon by force. Okay. The second, when a body is acted upon by a force, the time rate of change of its momentum equals the force. Okay. And the third, you have if two bodies exert forces on each other, these forces have the same magnitude but opposite directions. Okay? So the first one, okay, if we write out an equation, we can think of P as being a vector that describes momentum, and we have a mass and we have a velocity. Okay? So what we're saying is that we have the opportunity for something to just kind of keep going unless something acts against it. And for this equation, maybe it's a rhetorical question, does it describe linear motion or does it describe rotational motion? And of course, it's linear motion. Okay? And then what we're going to do here is we're going to look at what are the equations that we typically use for dynamics, and these equations are applicable to 3D applications in terms of linear motion and in terms of rotational motion. But moving forward, okay, again, we have an equation that we use for describing the linear motion, and we typically think of F, right, as being a force vector. We can say that P dot is the time-based derivative of momentum, which we describe as acceleration. Okay. So Newton's original description didn't come out immediately to say that F equals ma, right? But he said the time derivative change of momentum. And for the third law, you might see this in terms of, let's say that one is acting on two. Okay. Force, you have a force where you have one acting on two, then it's going to be the opposite of two acting on one. And I remember when I was in physics, and we were doing the third law, and pushing down on a table or thinking about that. It's like, oh no, I have this force of my fist acting with a downward force on the table, right? And I can just think of an opposite force as negative acting on the table as well. But no, these are supposed to be pairs. So you have one force acting on the table from my fist, right? And then I have a reaction force from the table acting on my fist. This does not assign, it's not just a matter of changing the negative signs or playing with them. Okay? And I got it wrong on my physics quiz. So in rotation, and fortunately for us in this class, we will not do much in terms of trying to conserve angular momentum or describe it. Okay? But we can describe angular momentum as maybe some vector L, and we have a moment of inertia I, and we have an angular velocity omega, and we can again think of omega as being a vector. In respect to the second law, okay, we can think of a torque as being equal to some moment of inertia times the derivative of angular velocity, and that angular velocity with its derivative is what we call angular acceleration. Okay. And then in terms of these two bodies exerting opposite forces on each other, there's not really a good analogy, okay, that we can think of when it comes to momentum. And we can maybe kind of think of reaction torques, okay, but from a theoretical perspective, there's not a wonderful analogy. But I mean, I could write that like I have a torque 1, 2 is equal to a minus torque 2, 1. Okay, but from kind of a more purist perspective, you say it kind of breaks down here. Now, if we're doing statics, what about these equations is relevant to us? Yes. What's that?
Third one, right?
Okay, so the third one is relevant? Yes, absolutely. This one's going to be relevant. Okay. In its entirety, in fact. Okay. What else is relevant here? Yes, Isaac, you're thinking. You're pointing.
Torque?
Okay, so this one you're saying?
Yeah.
Okay, torque is equal to I omega dot. Okay, how is it relevant for statics?
So when we think of momentum, probably like, wait for statics?
Yeah, no, yeah. I'm not disagreeing with you. I agree with you that it's relevant. Okay? How is it relevant? You're right. I would say that one, two, three, 4 are very relevant. Okay, but I want to ask how are they relevant? Yes.
So the second and its analog are going to be relevant because there's no angular or no linear acceleration, so net torque needs to be 0 and net force needs to be 0.
Yes. Okay. So in these cases, right, what happens is essentially omega dot is 0, right? And that means that this right-hand side is 0. What I might have said in better terms is that these are resultant torques and these are resultant forces. Okay? Alright? And so when you see these equations, you're like, oh yeah, that's just for dynamics. No. We're talking about summing up the forces and torques, right? So that they end up being 0. And then yeah, this is I mean you've kind of maybe 1, 2, 3 are really relevant because these we're going to say we have constant velocity or constant angular velocity in some cases, but we're usually going to be thinking about forces and torques more than momentum and angular momentum. Okay. Good. So we're familiar with these equations, right? The sum of the forces is equal to 0. And yes, we had torques, right, on the previous slide, but now we're saying that we're going to think of them as moments in most cases. For like beams, okay? And even when we talk about shafts, you can think about them as moments instead of T's, all right? We'll go through that a little bit more detail today, but you already saw some of that yesterday, right? Because you saw, oh, we have this torque, and then we got to think about how much more torque it can support. So when you think of this vector force, or you think of this vector for moment or torques, what did you then immediately write, or what did you often write down in statics? You would break it down into scalar equations, right? And what are those scalar equations? Those scalar equations are just sum of forces in the x direction, right? Is equal are equal to 0, right? And the sum of the forces in the y direction are equal to 0. Sum of the forces in the z direction are going to be equal to 0, right? And similarly, you would do that for the moments. Okay. We are working in more or less a 2.5D world for this class. Okay? In other words, most of the drawings that we're going to be using can be drawn in boxes and circles, kind of. Okay, shafts, yeah, we have to do maybe a little bit of a 3D illustration, okay? But until we get to combined loadings, most of what we're talking about is in 3D. So just as an exercise, if I draw something like this, and we're going to cover cantilever beams in more detail. And I draw my coordinate system kind of like that. Okay. First of all, any questions on this? X and Y, no, right? Which direction is Z coming or going?
Out of the board.
Out of the board, right? And if I wanted it into the board, I would have drawn an X. Okay, so you remember that from physics. Okay, if I think about the forces that I have in this beam, along this beam, all right? Which direction are the forces? Yes.
The negative y direction.
Okay, so you have a P in the negative y direction. What about at the wall? The wall acting on the beam. That's going to be,
That's gonna be Z.
okay, so the force, I didn't say the moment, I'm saying the force. If I've got this force acting in the minus y, alright, Can I-
There's also gravity.
well, okay, if I have gravity, sure, but let's say gravity's acting in the y, or minus y, right? I didn't draw gravity, right? But if I had, I probably wouldn't put it in the z direction for this particular geometry, unless I wanted to be fun, right? So, typically, right, when you have a force being applied to the system in one direction, the rest of the forces you're going to be dealing with are going to be, plus or minus that same direction. Now, what about the moments? Which direction are we thinking about for moments in this problem?
Oh, around the Z-axis.
Yeah, so in Z, right? So there, right? Let's say we have a moment, right, being applied on this end, given its length, I didn't specify length, right? I'm going to have a reaction moment at the wall, and it has to counteract the moment, right, from this. So this is gonna want to make this thing go, and it will. We'll eventually talk about displacements near the end of the class. So there's a reaction moment, right, that's going to be acting this way from the wall on the beam. And which direction do we say that is? You got a 50-50 chance? Is it positive z or minus z?
It's going negative z. From the walls.
From the walls, from the wall onto the beam, right? So if I have, now I redraw, right? And remember, a lot of times these things are arbitrary, right? But I'm going to draw it like that, okay? And we'll call that MR, okay? And let's say there's also a reaction force. We'll call FR there, right? Now you could have drawn these opposite directions, okay? Nonetheless, right, this reaction torque is what is keeping, a reaction moment is what keeping the beam, right? The beam would just go down this direction, right? And so what we have here, all right, is a reaction moment that's actually right hand rule coming out at you. It's acting on a positive z. Okay. So we'll do this in more detail, all right? But I just wanted to take a moment. You're like, oh, these are really, we have to. I still have kind of this wish, because you'll see me make mistakes during the semester or during the summer, right? I had this wish. It's like if I could just know which direction is positive and which direction is negative, my life would be so much easier as an engineer. Okay. All right. So what we're going to attempt to do today is, again, talk about the three primary structures and discuss the forces, the torques, the forces and the torques, or the forces and the moments, or the forces, okay, that are involved. All right, what are we talking about here, right? The bars, of course, normal loading, okay? They're fun. But you'd be like, wait a second, there's going to be a little trickiness. Shafts, we're going to say those have torques involved with them. And we're going to be thinking about internal torques. We're going to also be thinking about internal forces. Beams, as you know, that we just saw, they have both forces and moments involved with them. And we'll be looking at the internal forces and internal moments. And trusses, right, the way we design these with the pinned joints, they are all going to have just axial forces inside of them. Okay, so let's talk about how you perform an analysis. All right, like, oh man, we did this so many times. Okay. When you have a problem, and you're doing it in statics, eventually we're going to do problems that involve statics, material properties, and geometry. Right now, we're kind of thinking a little bit about geometry, but we're just really doing statics. Right? So this is like some of the forces, some of the moments, those have to be equal to 0. Okay. Nonetheless, what is the typical process? And it's okay if you looked at the slides previously. How do you attack, if I give you a bar, and we say, okay, we want to evaluate the internal force in this bar, or the internal forces in sections of this bar. There's a two-prong approach to this. What do you do? What's the first thing? Yes, Karen.
Free body diagram?
Okay, so free body diagram, that's a good. Actually, there are going to be multiple free body diagrams. Okay, so yes, good. Free body diagram, okay. And what is your first free body diagram going to detail? Yes, Isaac? Yes, the forces, good.
There's no moment in this, is it?
No moments, right? We're doing bars, all right? Yes?
You do one just for external forces and one just for internal forces?
Correct. All right, so first we got to perform external equilibrium, all right? Big, please do it, okay? You just please do it, okay? And with that, okay, it's highly advisable to create a coordinate system, okay? So first we're going to draw. I mean, this is exactly the same thing, all right? It's nothing big, nothing shocking here. And if we define a coordinate system or axis, maybe we'll call that plus z. But this is the coordinate system that we're going to use for external equilibrium. You don't necessarily have to have the same coordinate system when you go to internal equilibrium, all right? We'll get into that a little bit, okay, in a second. But you're going to need a coordinate system. You're going to apply Newton's second law. You probably don't have to circle it, okay? It's like, yes. And Newton's, the appropriate law here is that the sum of the forces is going to be equal to 0. And how many forces are acting on this bar? Huh? 2, right? One on the top, one on the bottom. Okay? This is external equilibrium. Somehow I've made a bar that just floats in space. Okay? Because I've perfectly balanced these two forces. If not, it would be accelerating. Okay? And so this is very trivial. Okay? Now, what do you do when we think about internal equilibrium? We have some jargon that we use here, or we go to Pizza Hut or some other pizza place. We have a lot in New Jersey. Gerlanda's. Huh?
Slice.
Slice, right. Yeah, there's an app. I didn't know there was an app about that. Okay. But so we take a slice, right? That's the app. That's what we do, right? So we take a little slice, and this is me trying to be cute by making jagged sliciness. All right. And we then look at a balance between the external loads and the internal ones. Okay? Now, a lot of times when we do this, we might be wanting, for whatever reason, to redefine a coordinate system. That's okay. Often, if you're going to do that, okay, my choice would typically, if I'm going to create a new coordinate system, it's to say that whatever slice I have a positive coordinate coming out of the face, right? So you don't have to necessarily do that, and in this case, it's pretty trivial, all right? But it's sometimes helpful, okay, to define a new coordinate system, or at least remember what the old one is. Well, what is the internal force, F1 or N here? What do y'all think? You only have really one other option, right? Okay. And for this thing to be, so you have to apply equilibrium again, right? So this is essentially saying, okay, I've got my second, okay, so here's the coordinate system like we talked about. And then we apply the second law again, right? And we have that if I've got it defined this way, I've got N1 minus F, which is this F down here, and that's N1 is equal to 0, so N1 has to be equal to F. Okay, so yes, free body diagrams, first do external equilibrium, then move to internal equilibrium. Take a slice. Now, did I have to slice it this direction to figure out the internal force? No, I could slice it where I keep the top, okay? And then I have a force coming off the bottom. And of course, N2 or F2, right, is going to be equal to F, okay? But see what I did here? I created another coordinate system where it was coming out positive from that face. Okay, often it's a nice idea. Now, you tell me, Is N1 equal to N2? Yes, I see some nods, so that's good. Are they drawn in the same direction? No, they're not. Okay? But they're the same. Okay? You know, one way to think of this is if I took another double slice, okay, and I said, all right, I'm going to think about the internals, right? This looks exactly like the same figure that we just have, or the same figure I drew previously, right? But these forces are the same, okay? And when they are coming out of the faces like this, we say it's in tension, right? And we're going to talk a little bit more about that in a second. Okay, but this is often a confusing point. Okay, so they are acting in opposite directions. And so you're like, well, maybe they're different. They are equal in magnitude. Okay. And they describe the same behavior. So you're going to see systems, you already know systems, right? Where if you slice the beam and you leave one side open versus you slice the beam and you leave the other side open, we have some conventions we'll talk about, will remind us about. And those, even though those moments are in opposite directions, those forces are in opposite directions, they are describing the same behavior. Okay? And so it's very important to keep these straight. Now, like we were saying, if N1 and N2 are greater than 0, the bar will be in tension and it will be stretching or straining apart. Okay, so you can think of this as the cable. And even though we don't have relationships yet, but we'll start to at least think about some. We'll think about these bars and shafts as springs tomorrow. Okay? But you have an intuition, right? You know that if I pull something apart, it's going to stretch. Every 2-year-old probably knows that. And if N1 and N2 are less than 0, the bar will be in compression. Okay? And the top and the bottom are going to be getting closer to each other. When we say N1 and N2 are less than 0, of course that is assuming that we've drawn them to be coming out of the face that we've cut. And this is a trivial case in many respects, right? But if I had these purple F's, right, acting inward, and they were positive, that would also be an example of compression. Okay. Any questions on this? Thoughts, comments, or criticisms? Okay. Yeah. Now, this is kind of the same thing, just saying that we have sign convention, all right? So not really much different here, but saying, hey, look, we can also relate these to the external loads, which we just discussed. And again, if we put the external F's or the internal F's acting inward and we make them positive, they're going to be in compression. Okay. Good. Okay, now we're just going to get a little bit trickier. What happens when we have multiple loads on a bar? Do you all remember this? Kind of vaguely? No? You covered it in statics, I think. All right. my drawings may be funkier than the ones that you've seen in textbook, but they mean the same thing. So, what are the internal loads between A and B, between B and C, and between C and D? Okay. And based on what we just talked about, how would we go about solving this problem? What would we do? Yes.
You do
Inter-
the sections or slices.
Okay, good. All right, so we got to use the slicing, okay? And before we do the slicing, yeah, we might have to do external equilibrium. Actually, you should do external equilibrium, okay? Even if they give us FA, FB, FC, FD, right? If they give us all four, we should make sure that when we sum them up, they equal to 0. Okay? More likely, as you'll see on the homework, I'll give you 3 out of 4 or 2 out of 3. First, you had to figure out the unknown external load, and then you get to figure out the internal loads by slicing. Okay? So, external equilibrium is first. And again, it's not a bad idea to define a coordinate system. So let's say this is plus x in that direction. If this is plus x, what does the external equilibrium equation look like here? Well, first off, what are the external forces? Andrew, you want to give it a whack? Oh, sorry, Joshua. Andrew, Joshua. Okay, go ahead. Right. Okay. And then how would you write an equation for static equilibrium for the external static equilibrium for this, given our coordinate system?
FE plus FC
Good.
plus FD minus FA.
Good. Exactly. Right. So we're going to sum the forces in the x direction, and we have either putting a minus FA or putting a minus, however you like it, right? This is pretty simple. Okay. All right. So then, let's say that we first are interested in the internal force between A and B. Who wants to tell me how to do that? Okay, go ahead, Andrew.
So you make a slice between A and B, and then you have the internal force pointing out the slice that you made.
Okay. Now, which direction you want that face to be facing? Left or right?
Right.
Okay, yeah. You could choose either, correct? You can choose either direction, but I agree with you that it's going to be simpler to have it facing out to the left, right? So what are we talking about? Okay, we're going to draw, and this is my little face, all right? And so this is the slice right here, and I'm opening to the right. And so that means that my internal force, because I choose it to be in the positive direction of this face, yeah, that's kind of our convention here. I say that's FAB, and I have FA going in the opposite direction, because that's the external load. Okay? So this one is pretty trivial, right? What is FAB going to be equal to? And FAB means, right, that means the subscript just means between A and B. Okay, and that's another important point. It doesn't matter if I'm here, or here, anywhere in between A and B, that force is the same. Okay? It's only when I jump, right, into this next area, or into this next area that it changes. Now, if I have gravity acting along this, right, in the x direction, then we've got a different story. Okay, but right now all I have is these discrete the lobes. So FAB is equal to FA, right? What's the alternative way to do this problem? Oh, first, let me just, okay. Yes, so this is this, yes. Okay. This, right. So what would be the alternative? Just to figure out FAB. What's the alternative?
Take a section the other way.
Yeah, so you take a section facing the other direction, right? So now I've got a direction there. And Jeff Hansen, so if if anyone doesn't like this class or the way it's taught, just go watch Jeff Hansen. All right, I'm okay with that. And you'll see even on the website, we got links to his videos. All right, I'm a fan. Okay, so he has what he calls the cover-up method, right? You recall? Okay, so we would cover up this side, right, and then we have an arrow coming out or vector coming out, okay, that describes FAB. And in that case, right now I've got FAB going in that direction, FBC going, or FB going that direction, FC going that direction, FD going that direction, right? So I have essentially FB plus FC plus FD is got to be equal to the FAB, alright? So similarly, maybe this is more easy, it's easier to see, right? If I'm interested in FBC, right, then I can take a slice here, and now I've got FA and FB to deal with. And I can write out the equilibrium here. And notice, right, these are in the same direction. I've defined a new coordinate system. In fact, I defined all these coordinate systems, but they're the same as the original. Okay. And then we can say that FBC is going to be equal to FA minus FB. Okay. And then similarly, if I'm interested in figuring out what FCD is, okay, I can write it out like this, and I have my FCD is equal to FA minus the FB minus the FC. And if I want a shortcut, alright, FCD, I can take the slice, cover up the left side, and then have just FD, right? So these are the same things. These are the same, right? These FCDs, but it's a lot simpler if I already know FD, which I probably would have, because I would have done external equilibrium first. Okay. Any questions on this? There are some opportunities on the homeworks to do these types of problems. Okay. So, speaking of that, yeah, so these are the, okay, so that's question 1 on the homework. Okay, and question 3 on the homework. Actually, question 2 got out of order. I'm sorry, so you might want to come back to it or skip it and then do question 3. Okay, question 2 is on beam bending. Okay, all right, and then there'll be a question about, okay, is it in tension? Is it in compression? Okay, and what is the sign? Okay, so now well, if we have time, we'll come back and we'll do these. But I think you've got the tools at this point to be able to have these types of problems. So let's go ahead and shift our focus to shafts. So here's a lovely shaft. I've just kind of tried to do my beautiful art at a slight angle. And same thing, and calling one side A and one side B. The process, again, external equilibrium first, internal equilibrium next. Okay? And if we're doing external equilibrium, what is the equation that I can write? There's really only one equation I can write here. Yes.
Negative TA plus TB equals 0.
Right. Okay. Now that's interesting. Well,
Well, it depends on what.
exactly, right?
Yeah.
So how did you define, when you said that, how did you define your coordinate system?
Actually, it should be flipped the other way around in my head, but the way I defined the coordinate system was generally in statics, counterclockwise is considered positive. So in actuality, TA looks like it's going counterclockwise, so that should have been positive. So I would write positive TA. TB looks like it's going clockwise, minus TB equals 0.
Yeah, okay. So what you're saying is, let's define TB as being positive. If that's the case, what is, and let's just say it's like, whatever, X, Y, Z, but which direction then would that coordinate axis be in this system? If TB is positive, which direction is the coordinate system?
So positive Z is going from TA to TB.
Correct.
Direction.
Okay, so it'd be coming out of the TB face. All right, that's not wrong. Right, external equilibrium, fine. Okay, did I choose that? No, but that's fine. Right, what did I choose? I chose coming out of this face, but it's fine. Either way, you're gonna get the right answer. Okay, so you get, the way I think of it, put this right. I think, again, TB minus TA equals 0, TA minus TB equals 0, right? Tomato, tomato. Right? Actually, I don't know how that's quite the same thing, but anyway, you get the point. All right, you're gonna get the same answer, and these two better be equal to each other. So now, if we take a slice. Alright, do you see this is analogous to what we did with the bar? It's like exactly the same thing. Okay? We have the option to leave TA and cover up the right side, or kind of the right side, I don't know, the right side here, or the into this portion going in more into the board, right? So now this is exposed. What's your choice? What do you think you, now I have a stronger recommendation than I had last time. How should I write what we'll call an internal TAB, an internal tab? How would you draw it? How would you define it before you do the output? Let's see, Sharif, how's it going? So how would you define the TAB, this internal? Not sure? Okay, that's okay. That's fine. That's great. Let's see, your name again is Matt. Yes, so Matt, how would you go about doing it?
TAB would be going clockwise.
Okay, relative to what?
What would be negative? The negative direction.
Okay, relative to what? See, this is tricky, right?
Z
Okay, and which way is Z?
squared.
Okay.
Well, it's like-
Okay. So this is good. All right. So you tell me, do you want your local coordinate system to be into the board? Can we agree on that? There's into the board and the out of the board here.
Is Z in out of the board?
Okay, so Z was out of the board here, right? What did we say a minute ago about the bars? When you're defining a coordinate system and you cut a face, which way is advisable to draw that coordinate on the bars? Anyone remember?
positive direction coming out of the slice.
Yeah, coming out of the slice. So typically here, as we define a local, we want to have it coming out of the face. Alright? So that means, I think, maybe I confused you, Matt, because I think you said, I want it to be clockwise.
Mm-hmm.
Alright? So I'll say, okay, fine, we'll call it clockwise. Alright? Because I'm going to say that we have a plus z in this direction. Okay, so this is coming out of that broken face. And then I grab it, right hand rule, thumb that way. I'm going to say that it goes that way. Okay? That makes sense? Any questions on that? So again, using the same principles that we used before, where we said, okay, take a slice, have a vector come out of that face. Here we're doing the same thing, but now we have a shaft.
Wait, so
Yes, Isaac.
how, like, you see how on the top, you say the positive z is this way, now you flip it and switch it to the other way?
Yes. You do external equilibrium, you have the opportunity to define a coordinate system. When you do internal equilibrium, you have an opportunity to define potentially the same coordinate system or another coordinate system.
So they both can be positive?
Well, yeah, you gotta define a positive direction of a coordinate system, right? So yeah, they're actually in the opposite directions. Okay. Yes.
So in summary, you can define it to be in either direction. You just defined it positive one way and then positive another way to just show us what it looked like.
I'm gonna take a firmer stance. Okay. To keep us from getting confused, try when you take that internal slice, define the direction coming out of the face as positive. Okay. Here I have two faces of my slice, right? Here I have two faces. I can choose that face or the other face, right? It doesn't matter for external. Okay? And that's another thing we'll talk about. When you choose the direction of the reaction forces and torques and externally, you should choose what just you think makes sense to you. And I'll explain that a little more carefully when we get to beams in a couple minutes. Okay? But here, I'm going to be more assertive. I'm going to say, to keep yourself from getting confused, make your coordinate system positive coming out of the face that you slice. Okay? It's a good convention. It's a good convention to keep. Right? Even if you're slicing a beam, we don't always think of the normal load coming out of that face, but sometimes we have an axial load on a beam. Okay? And it's good to think of it as positive coming out of that face. Other questions on this? Again, my wish has often been that I just know which direction to draw the arrow. Is it positive or negative? Okay. So from here, right, how would you write this equation of equilibrium? Okay.
TAB minus TAB 0.
Say that again.
TAB minus TAB 0.
Sure. Yeah, I'll do that because I'm going to say that I've defined my TAB to be positive, right, in the z. So I'll say TAB minus TAB equals 0. Is that what you were going to say? Back. Okay. Good. Okay, and your name in the back again is
Nasir.
Nasir. Okay, Nasir, and right in front you are Kadia. Okay, so then that's that. Alright, if I take a slice, okay, and I expose this one, right, then obviously the z comes out this direction, and then I draw it appropriately in the positive direction using the right hand rule, which means it's going to be counterclockwise, okay, like Matt was getting at. And it's clockwise up here. And I didn't even rewrite TAB. It just happened to be very nicely the same. Okay? And of course, now I have TAB minus TB is equal to 0, and I have that TAB is equal to TB, but Okay. The next slide has us thinking about, can a shaft be in quote tension or compression? Well, tension and compression are force related terms, right? So not really. Okay. We can think a little bit, all right, about, okay, if I'm twisting, if I'm twisting in one direction versus the other direction, and if it's TAP negative or positive with respect to the space, that's what we can talk about, okay? But we don't have kind of the same terminology, okay, with compression or tension. And part of that is the mechanics of why things break, and we'll talk about this later. Do you think a material cares if it's under compression or tension in terms of whether or not it breaks? Yes. Why? Why do you think maybe it cares? It cares. Can a material care?
I'm imagining a bar in my head. If
Yeah.
I pull it this way,
Yeah.
eventually it'll break it apart.
Right.
But if I compress it, I'm just pushing it further into itself.
Right. Okay. And so when it comes to, okay, so there are a few things. Nuances, right? I agree. Okay. When it comes to a material plastically yielding, it depends a little bit on the type of material. Okay, it turns out the brittle materials typically have a higher strength in compression than they do in tension. Okay? And they typically fail because of these normal stresses, okay? These normal forces and stresses, or normal force applied over an area. The ductile materials, on the other hand, they actually typically fail because of an equivalent shearing. Okay? And this is going to be the first time we kind of describe what shearing looks like. Okay, but those materials, they don't care if I'm shearing this way or if I'm shearing this way. It's not the same as am I in compression or tension. Okay? And so we don't really we can describe, okay, which way is the torque, internal torque, okay? And we can think about an orientation, we can think about what the deformation looks like, but the material is not going to fail differently based on the direction of twist. Okay? Whereas compression versus tension could have an effect on the material. Okay? So what would the deformation look like? And this is my crummy little drawing to show. Okay? We have a shaft, and if I put a grid on it, like that, okay, you can then begin to think that this grid originally has all 90-degree angles. But then, if I apply torque, or a balanced torque to this system, and in this case, you tell me, which way did I twist it? Oh, okay, here, I should have paused it. Okay, which way to twist it? I twisted it so that this face is going the counterclockwise direction, right? At least us looking into it, and this is going the clockwise direction. And you can kind of see that that grid is no longer square. Okay, so like if I were to, I don't think this will work. Take something like this, okay, and you see they have nice right angles, and then I begin to twist it, you can kind of see that the angles, it gets deformed, all right, and it's no longer right angles, okay. This is our first example of what shear strain looks like, and we'll do a whole day on strains, normal strains and shear strains, okay? But actually we won't do a whole day. We're going to do stress and strain. Okay? But we can think about how the system is going to deform, and that informs us in terms of the direction of these torques are being applied. This I think is useful, okay? Because what will happen, right, is if I have this little box, right, and now I draw another little box, okay, right here. So I took, this is the same box, right? Do you see this? This side, I'm saying the left side, this left side has shifted up if I'm looking down on it relative to the right side. Okay. And this top has kind of done that, and this bottom has also done that. So if you had to draw forces on this, now we're getting into what are really stresses, how would you draw arrows here? How do I go from this to this?
If you draw forces.
Let's say it's not an infinitesimally small element, blah, 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 blah. Yeah, if I were to draw forces acting on this box to go to this box, how do you draw it?
One going down.
Okay, on which side?
Like, you see the spin? Like, it's going face down.
On this side? You're going to say it's facing down on this side? Yeah, I would say that, right? And then one's facing up on the other side, right? Yes. And so those two are pretty intuitive. And we will show that by equilibrium, then these arrows need to be going these directions as well. Okay? Otherwise, this thing would rotate. Okay? And that would not be statics. Or it would accelerate. It could have angular acceleration, and that would not be statics. Okay? Okay, so torsion results in shear. This is our first, I guess, example of what shear looks like. Shear didn't change the volume of this rectangle, at least for small shears it's not supposed to, but it did change its shape. It deformed its shape. Okay. Now, if we have multiple loads on a shaft, what do? First, we do external equilibrium. Okay. We define the coordinate system. Then we perform, we do second law, right? We define the coordinate system, we do second law, we draw everything out, and we do the same thing we did previously. We take a slice in between, all right? And if I'm interested in tab, TAB, right? I have a slice that I can take in this direction, right? Facing, with the other one facing into the board, okay? And we've already kind of seen this story in that what direction I should have the arrow acting. It should be coming out of this face, and it should be then, having tab going, following the right-hand rule, so that's a positive torque. And we can run with the simple algebra so that we know that the TAB is just equal to TA. Okay. If we go down and now, or up, however you want to look at it, I guess. Yeah, we go down the line or we go up here, right, and we're interested in what the internal torque TBC is, right? Again, I'm going to define this to be positive, that phase. And we've got an equilibrium problem, right? What's the equation here? Let's see, Alexis. How would you write an equation to describe relationships between TA, TB, and TBC?
TB is TBC will be positive and TA is negative.
Yeah, right? And then that's going to be equal to 0, right? Exactly. Good. Okay, so TBC plus TB minus TA is equal to 0. And another way to write this one out is to slice. Right, so now I'm taking the slice facing the other direction. This is TC, which is at the end. I'm now defining a new Z that is coming out of this space. And TDC has to be in that direction. Okay, these are the same. And TDC will just be equal to TC. All right, and well, TC is equal to TA minus TB from external equilibrium. All right. Yeah, so what's next? The beam. All right, so let's say that we have a beam of length L with force P acting on it, which we kind of I drew, briefly at the beginning, just to get us thinking about directions. What's our process? First, external equilibrium. Then, internal slices. So, with this, once again, we wanted to describe or define a coordinate system. And this is a pretty typical one, right? Which is what I drew at the very beginning as well. X along it, Y, normal to the beam, Z coming out of the board. Again, kind of a review, but how would you draw the forces and the moments on the external ones on this beam here? What do we say at the beginning? Anyone remember? Dylan, what do you think? How do we draw the external loads? We can use loads, right, to mean both moments and forces.
So P would be the negative y direction.
Good, yeah, I agree with that. And it's acting on the right side.
And then the reaction from the wall would be in the positive direction on the left side.
Yeah, okay, that's fine.
Would there be moments?
What do you think?
I think so.
Good, I think you're right.
So there would be a moment on the right side in the going into the board, so in the negative z direction.
Okay, well these are external. So what could possibly, if I drew this up here, Dylan, and I'm saying there's external, I didn't draw an external moment there. So can I have an external moment on the right side? Being applied, these are external. Not unless I draw it, right? So there's none there. Okay, but what on the left side? What about on the left side?
No.
Well, yeah, the wall can. The wall can. Right? So the wall is going to. This is a wall.
All right.
Right? And so, in order for this system not to spin, I've got to have a moment there. Okay. So, for example, right, if I just take this nice beam, right, and if I just have a pin, right, which I can't really do, right, it's just going to go like this, okay, like that, because, well, it's got, or, even if it didn't have gravity, if I put a force here, right, it's going to go like this, it's going to start accelerating around. So I have to have a constraint that keeps it from spinning. Because that pin can, in this position, right, that pin will apply a force. And it'll keep it, but it won't keep it from spinning. Okay? So the wall is providing that constraint. Now, do I have to draw those force and moment in those directions?
No,
No. Why not?
because these were external.
These are external.
Is it because like the pen or the like wherever it's hanging on, once we find out which one is positive, we could find out like we could switch out the P in forces like the resultant force.
Okay, so yeah, you can. I think what you're getting at is I don't really know which direction these things are operating. I mean, I do because I've done this before, and you probably do because you've done this before, and you also you've lived in this world, so you know that if I have a force acting on one end pulling it down, there's got to be a force somewhere else pushing it up. Otherwise, it's going to fall, right? So that one's maybe a little intuitive. Even when we first introduced this a few minutes ago, or an hour ago now, right? This was like a little bit confusing in terms of which direction that is. It does not matter, okay, with external forces. You can pick whatever you like. I try to pick what's convenient, all right, because I like positive numbers better than negative numbers, less writing, okay? But I think what you're getting at, Isaac, is that yeah, once you do the equilibrium, it'll work itself out. You'll get either negatives or positives for these reaction forces and torques, okay, or reaction force and torque. Okay. So when we apply Newton's second law here, okay, now we have to do the summation of the forces and the summation of the moments are going to be equal to 0. Okay. And in this case, we have summation of the force in the y direction is equal to 0, and we have the summation of the moments, and we're going to say that these are about the z direction. Okay. And we also, okay, remember, forces, you don't really, forces you have a direction of all these forces, but you don't have to pick a location, right, about which the forces are acting. But for the moments, you better, okay? You better pick a side or a location. Usually you try to pick a side or location that's convenient, that allows you to eliminate one of the forces. Okay? In this case, since Fr is an unknown, I pick the left side. But you could pick the right side, and then you don't have P doing anything, right? But you know that P is equal to Fr, so it's not that big a deal, right? But again, often you want to be strategic. So when we do the sum of the moments, right? Now again, this is external, and it's acting here. Okay, we have to think Z is coming out of the board. Mr follows the right-hand rule, so that's going to be positive. PL, though, on the other hand, right? So this is a moment being applied to the system, right? R cross F. Okay, but we usually don't write. I don't write many cross products in this class. Okay, but you're gonna. That's going to be the PL that you see there. Okay, and so MR is equal to PL. Okay, so now what do? We need to follow our same procedure, which is to slice. We're going to use a slice app. Okay. And we're going to use the method of sections. We're going to attempt to define a coordinate system. All right. And again, often it's good to have that coordinate system coming out of the face. Now, in this case, with the beams, right, you remember that you typically are going to define it, though, as having a location that is starting at some type of boundary condition. Okay? So this X is coming out of the face as it was before, okay? But it's, I would say, you know, locate it somewhere, which is probably, you know, at the wall. Okay, bless you. Okay, so now, Marissa, sorry, is that me because you're sneezing? All right, but Marissa, what do I do here? I've taken a slice now. What are the loads that I put on this open face?
The moment would be going counterclockwise.
Oh, okay, good. That's good. So you're saying we should define some type of internal moment here. Okay, and I agree. And then you can kind of look down here, right? Okay, and it's like I accidentally left the convention. Okay, so yes, we do have a convention, and we follow Fiddler's convention. Okay, when I was taking this class, or the equivalent of it, as an undergrad, we didn't use this convention. And when I started teaching this class, I'm like, this seems really funny. Like, why is V going down on the right? And I look back at the old book, I'm like, oh, that's why. Because the way I taught, the way I learned it was with a different convention. Okay? So the convention that we use here is that if you have a right side being exposed, V is going down and M is going to be counterclockwise. If you have a left side exposed, then it's the opposite. So just, you know, even on your formula / example problem sheet / whatever you want to write sheet for your exams, probably not a bad idea to write this somewhere, just in case in the stress of the moment you forget the convention. Okay, and then we apply Newton's second law. Okay, and we have the sum of the forces in the y direction is equal to 0, and we have that FR and B are going to be the same. And we have that the moments, again, you gotta pick a location, pick the left side here, which, I don't know, really, because again, right, you might want to pick it here because then you don't have to care about V, alright, but whatever, you can do either way, alright, so here you, MR, right, is positive, and M, the internal moment, is positive. And XV is a little bit, that might be a little bit tricky, right? But you gotta think, oh, okay, this is the R, this is the F for the V, R cross F, for R cross V. In this case, okay, it's going to be contributing a minus, negative moment, right? It's going in that direction. I guess I should have probably said that when I picked the coordinate system, let me just add this, we're saying that Z is coming out of the board. And if we do the math here, we can get a relationship for M, and whoops, and that's that. Okay, so this is kind of the classic formula. Notice a couple of things. One, this moment and this V, we describe them as a function of X. So I'm moving the slice along the beam. Okay, and that's what X is giving me. If I have X equals L, what is V? What is the internal shear force? At X equals L, what is the internal shear force? Shear force, actually, it's always P.
Sorry,
Right.
let's look at the moment equation.
Right, you're looking at the moment equation. I'm getting there, okay? So now, Eric,
Sorry.
if the moment, we're looking at the moment, and I have that the X is equal to L, what is the moment?
0.
It's 0, right? And that makes sense, right? We said there was no moment being applied on the right side, okay, by a reaction, right? And remember, I can take a slice just like I sliced exposing. If I come over here, right, and I've got a P, and remember I'm using my convention now, and I've got an M, and I've got a V. That's not really usually how we write it, okay? Right, remember that M and that M is the same whether I'm coming from, whether I'm exposing the right or the left. Right? This is just like with the shafts. Okay? If I'm, so I've got right here, and I'm like really infinitesimally close to the right side. That would be x equals L, right? So there's like nothing there. And what's the moment being applied there? Well, there's no moment being applied there. So M has to be, you know, if I do the equilibrium of the moments, M has to be equal to 0. Because there's no moment applied at that right side. But if I move it along this direction, okay, then I have some length of this, right? So that means that P can contribute a moment, and that's going to be getting more and more negative as this equation indicates. Okay? So much so that when I'm at the left side, oops. Right, at the left side I've got MR, and again I've got FR. Wah! Oh man. Okay, well anyway. What did I just do? Okay, MR, yeah, I just like jumped a lot. Okay, so I got MR here, I've got my FR here, right? And I've got my V, and I've got my internal M. And this was the X, right? Going that direction. So when X is equal to 0, and I do the equilibrium right here, look, MR positive plus M, right, because M is positive, equals 0. Right, that's equilibrium. So when I do that, and V does nothing because X equals 0, right? That's just like going back to this stuff. Right, that's just going back here. So that means that MR, or M has to equal minus MR, right up at the wall. The internal moment has to be equal to the negative of the external moment applied to the system. Is that kind of clear? You've done these diagrams before, but sometimes it's good to have a review. So when we draw these, okay, as many moment diagrams, these are the profiles that we get. You remember this? All right? Looking familiar, right? Okay. And it's just plotting the equations that we solved. Okay. And what we're going to go on and do, you're like, wait, but I already did this. This is so boring. Why are we doing this? The reason we are doing this is because what you did in statics doesn't tell you whether or not this beam is going to break or not. But what we're going to tell you in this class is what are the stresses involved in this beam? What are the strains involved in this beam? What are how much does it deflect? We're going to tell you all those things. Okay? And that's powerful. That's powerful. Okay. Any questions? Any thoughts? Any concerns? if you want to use Colab to plot this out, you can. All right, it's very nice. Okay, but it's the same plot, same exact plot. Okay, and that code is available on the on the website if you like it. All right, we got to keep going. Okay, and so question 2 is essentially asking pretty much what we just did. It's very similar. Okay, question 5 is also going to be asking something similar, and in this case, what you're going to do is you're going to plug in the parameters to some of the equations that we already derived. Now, do you all remember distributed loading? Do you all remember and love distributed loading? Okay. Distributed loading was about how do you calculate what a resultant force might be and where it was located. Okay, so there's the math that you can see here in terms of both how to define this Wx, right? This is the distributed loading. It just defines this triangular function. And in this case, you have the rectangle function. So if this is like very queasy, go back and take a look in Hibbler's book. All right, it's there for sure. Okay. Never watch Jeff Hansen. Okay, that's fine too. So if we use some general rules, we can write, remember, a resultant force acting at the middle of that distributed load. So if it starts here, ends there, however you want to look at it, it's going to be acting in the middle. Okay? And we can figure out what the resultant force is by taking the distributed load, the max of that distributed load across it, and multiplying it by its length. Okay? And you get that value. Okay. Now, if you have the triangle, right? This one's a little more confusing. Okay. The resultant force is not so bad because, at least I don't think it's so bad because that's a triangle, right? So it's half base times height. Okay. So we can say that it's just going to be 1/2, if you have a W max over here, 1/2 max W max times L. Okay, and say, okay, it's not acting at the end, right? You say, okay, it's whatever distance it is starting from when it starts to pick up. And then the thing that's maybe a little more confusing is that we had to figure out where it's acting, and it's acting 2/3 away from where it's 0, or it's acting 1/3 away from the tall side. Either way, but it kind of makes sense, right? You're like, oh yeah, you know, bigger over here, that means the force is acting more towards the right. Okay, but the math spells that out. All right, if you do these integrals, all right, this is what you get. Okay, so we will make use of the distributed loads on beams and distributed loads. Actually, next time we'll do distributed loads in bars. Okay. Any questions on this? Of course, you know, you've got all this information, right? The slides, it's all there, okay? Now, the grand finale. Trusses. How much do you remember from trusses? Did you do a lot with trusses? A little bit? Too much. Okay, too much. Okay. It's here, okay, for your viewing pleasure. But the methodology is, again, first handle external equilibrium. Okay? And then you have two options. The method of sections is remarkably similar to what we just covered. But you also have method of joints. Does anyone remember what what these methods represent or how you go about them? Yeah. Anyone want to volunteer? A guess? Okay, sure.
Method of joints, usually you have a large structure with a lot of members and joints in between them.
Yes.
Method of joints is essentially a very long series of equilibrium equations where you take a joint and you draw out all of the forces, and you use the fact that some forces are directly opposing each other to write a bunch of equilibrium equations and solve your way throughout the entire truss. It's useful if you need to solve all of the members of the truss, all of the forces. Method of sections is very similar to what we were just learning before. It's useful if you need to find one particular section or member. And basically what you do is you take a cutting through no more than the number of members you would have equations for, so that your equilibrium equations equal the number of unknowns.
Wow. Okay, that was impressive.
I learned too much.
That was impressive. Okay, those are very good descriptions. Thank you. Thank you very much. Okay. So yes. So method of joints, right, has to first start with external equilibrium. Okay. So we first do the external equilibrium, and then we look at each node or each joint and look at all the forces from the members acting on those particular joints. Okay, so but first, right, here we have a coordinate system defined externally for the whole truss, and then we have reaction forces, okay, that we place on the truss. Okay, we'll get into these kind of roller type boundary conditions, but can we appreciate that this roller condition is not going to cause us to experience a reaction force in the vertical direction, and that this pinned joint up here means that we can have two, or we can define a resultant force from that pin in two orthogonal coordinates, or two orthogonal directions, okay, like we have here, AY and AX. And then this pin right here, this is a two-force member, where they're all two-force members, and since we have a force here acting on this direction, okay? This is external, sorry. I got ahead of myself when I said two-force. Okay. So that's the external equilibrium. We also had to use a little bit of geometry, right? So we know that if this is one length and this is a same length, right, then we have a 45, 45, 90, and so that we have square root of 2L. We use the Newton's second law, and we're going to have the sum of the forces being equal to 0. Okay. And then we can keep going, and look at the sum of the moments at a specified location, maybe C, all right, and can say that, all right, we have AX is going to be equal to P. So that's kind of useful information. Now, equilibrium of the joints, okay, means that we have to write out what's happening at each joint, as Kira was explaining. And with that, it's not bad to think about labeling the members as well. So the members being 1, 2, 3, and then saying, okay, we've got, these are two force members, force at each end, and we're going to draw a force that is coming in or out of a node, all right, and that we have some choice on. So we might not know whether it's going to be coming out of a node or in a node, okay, but if it's if I have a force coming out of a node, what are we suggesting that member is experiencing? The member associated, so like if I have F1 and F3 coming out of these nodes, is member 1, is member 3, at least if F1 or F3 were positive, is it going to be in tension or compression? Okay. So that would be the intuitive response, all right? If I have something pulling on this piece, it's pulling down. Does that mean that this piece has to be under tension or compression? Tension, right? Because it's acting on this and it's pulling it down. So it's what happens if you draw these diagrams, or if I were to draw this member here underneath, I'd have it showing a reaction, right? This member here. Oops. Right, would be like that. And this would be F1. Okay, so yes. So it seems like it should be under compression, and if this force were pushing on this member like this, then it definitely would be compression, but it turns out that it's pulling so that these forces, F1 and F1, are the same in opposite directions, right? This is the Newton's third law. Okay. So that's what's happening at joint A. Joint B, all right, which is at the right here, okay, that one has the P acting on it, which is external, and then I have to be consistent. Since I said that F3 was coming out of joint A, I've also got to say it's coming out of joint B. Okay, and right, we just said that this is supposing, right, that it's going to be under tension. And then joint C is going to have an F1, right, which is down here, essentially. Okay. So F1, which is going to be, again, coming out of the node, right? F2, all right, is going to be, we'll say, also coming into the node, because that's what we defined at joint B. I guess I skipped over that, right? So this member would be in compression, okay, and then CX is the reaction force. All right. So, whoops, wrong way. We have to apply Newton's law to all of these, right? And this is the painfulness. So for joint A, right, we can write it out as such. For joint B, and I'm going to go a little bit fast here, okay? I'm going to go way fast. I wasn't expecting you to get it. Do all this quickly, right? But you can essentially, we're summing the forces, right, at this node, and we're using information, right, from external equilibrium. We said that AY is equal to P and AX is equal to P, all right, and we're plugging these equations into our system. And I guess if maybe we should go back just to point that out, that yeah, AY is equal to P. We have an F3. Okay, we have an AX is equal to CX. Okay, and CX is actually equal to 0. Okay, so it doesn't come into here. Okay, so this is the method of joints. Okay, you do a bunch of algebra. Or Did you guys do this in any of your classes? You use MATLAB or you use Python or you use linear algebra. Okay. So one way, and you're not necessarily expected to know all this, right? But linear algebra or matrices are very useful for solving systems of linear equations. Is this familiar now? Alright. So because we can write 3 linear equations with 3 unknowns, we can then set them up in matrix form so that the coefficients for F1 are here, the coefficients for F2 are here, the coefficients for F3 are here, then we have F1, F2, F3, okay, so row times column, row times column, row times column, okay, and it's equal to this column vector on the right. Okay. And then you do the inverse, you solve, okay, for the inverse of this matrix, okay, and the resulting, and then you multiply that inverse by both sides, and you can get this column vector F1, F2, F3, and you can solve for the unknowns. Are you expected to do this on the exam? No, but I just wanted to point it out that this is a nice way. Now you have code as well with Colab that allows you to do this. And for assignment 4, there's one question where it says, please just type in this number, okay, and diameter for one of the members, and you'll be able to get the answer, okay? But there's not a homework assignment for this one that forces you to do, to use Colab, okay? All right, so when you solve those linear equations, we get that F1 is equal to 0, we get F2 is equal to P, okay, and assuming P is positive, that means that F2, right, was coming in to the node, which means it's in compression if it's positive, and F3, right, was coming out of the node, and if it's positive, that means it's in tension. We successfully solved, as Kira said, for all the forces in the system, right? For all the members. But sometimes that's not what you care about, right? And for that, we can use the method of sections. So method of sections is similar to what we've been doing up to this point, where you first, of course, do external equilibrium. Then you take a slice like you see here. You slice your system such that you either solve for what's the left or the right. Okay. And in that case, alright, I have these like exposed members, and we've already done the external equilibrium. We know that AY is equal to AX is equal to P, right? So those are these. And so we have all these P's right here. And what does this allow us to do? Well, it allows us to solve, or attempt to solve, for the internal forces in these two members, right? Member 3 and member 2. Okay, so there's member 3, there's member 2, okay? And we're going to apply Newton's second laws for some of the forces equal to 0 and some of the moments equal to 0. Okay, so in the x direction, we have P, F2, and we have, this is going to be either cosine or sine of 45 degrees, all right, which is going to be giving us a horizontal component. And we can also solve for the y direction. So we have a P, we have nothing down here, and we have, again, a cosine or a sine of 45, which gives us a component in the vertical direction for F3. And when we solve for that, that F3 is equal to square root of 2P, which is what we got last time. We also can now solve for F2, which is equal to P, which is what we also got last time. And that's it. Okay. we have essentially used this method, right, to solve only for the members that we sliced, and it was a lot less algebra. But we don't know, right? But we don't know what's going on in member 3, right? So we know we figured out what's happening in member 1 and member 2, but we don't know what's happening in member 3. So we could do another slice, right? Where we slice through member 3, and then perform equilibrium, and then that would be one way to attack that problem. Okay, so takeaways. First, do external equilibrium. Second, use method of sections. And if it's a truss, consider a method of joints. And you have all the tools. Any questions? Up here, okay? Let me go to the beginning, and I'll try to work some of these problems. Or at least get us started. Okay, nope. Okay, so, right. Here is the first question. Okay. It's asking, what is the internal force FBC between B and C, all right, in units of newtons, all right, and that's good because everything is in newtons. Okay. So what is it really asking us to do? How would you attack this problem? Sure, Eric.
First do external, so you can find out, whatever your unknowns are after you plug everything in.
Okay, that's good, right? So that's exactly what that green equation, right, at the bottom is kind of saying that we should do, right? So the first thing is we do external. Okay. And that equation right there, so we got to solve for FD, essentially, right? And we've got this equation right here. So that means that FD will be equal to FA minus FB minus FC, right? Because where is FD? It's not there. Okay, so that's good. Now, here's maybe the little tricky thing. Do I really need to know what FD is for this problem? No. I mean, you want to make sure that this thing is in equilibrium, all right? And so it's nice to solve for FD, but do I really need to? No. So it's like, this is okay, but only necessary if we cover up the left side, right? Because if we cover up the right side, all right, if we cover up the right side, what do we have? We're going to have a system, okay, where we have FA, FB, and we're going to define, how do you want to define the internal? FBC, how should we define it? What do you think? Yes, Andrew.
Pointing to the right.
Yeah, so it's probably not a bad idea, right, to define it. And, I'd be okay calling that positive. Right? So if we just do this out, right, we're going to have a minus FA, a positive FB, of positive FBC is equal to 0. Right? So FBC is just going to be FA minus FB. Any questions on that? Pretty straightforward, right? Okay, good. So the next question is, what is the force FCD, okay, between C and D? All right, so this one is similar. In this case, you know, again, I have two ways, but maybe if I expose the left side, if I cover up the left side, okay, then I really need to know what FD is. So then we have to do the external equilibrium, right? That's not bad. Alternatively, right? So this is FCD equals FD, you know, and we use external. Okay. The alternative way, right, would be to let's see, we have yeah, so just FBC and then FC, right, like this. Okay. And then FCD will be moving to the right, okay? And then I don't need to solve for FD, right? And FCD would just be equal to FA minus FB minus FC, okay? So that's how we approach that one. Okay, question, okay, what is the region CD in question 2 experiencing? So question 3, or session 2, question 3. So what can we say? The way we've defined it, FCD, okay, using our convention, all right, we'll say that this is the positive Z, this is positive Z, okay. You know, if it's positive, then it would be in tension, right? If it's negative, it would be in compression. So the middle two are not possible, the way we defined our FCD. So just look at whether or not it's positive or negative. If I'm not mistaken, I think it's negative. All right. Okay, keep going. Did I skip one? No, I didn't skip one. Okay, this is fine. So here we're doing a problem where we need to figure out what is going on in between B and C. Okay. So there are kind of two ways to attack this, right? One is I'm going to solve for TC at the end, right? So one would be, let's do external equilibrium. And I know that TC is equal to TB minus TA, just from this equation right here. Okay? And then what I do is I draw a little slice like that. Well, that was kind of crummy. Let's not even draw that. Okay, so TC is acting at the end. If I say that this is Z positive, which way do I draw it? Yeah, I see people doing this. Okay, yeah. So, so Divya, you commit? Okay, you commit. Alright, so it's going to be this way. And this is going to be TBC, right? And, well, if I do equilibrium TBC minus TC is equal to 0, so TBC is equal to TC. Right? So that's pretty straightforward. The problem can also be done, of course, by looking at exposing that side, right? And then we have TA and we have TB. And then this coming out over here is going to be TBC. It's the opposite. Actually, wait a second. Nope, I drew it wrong. It's this way, like this. Okay? All right, and so then that's going to be TBC plus TB minus TA is equal to 0. And you solve for TBC. Okay? Let's see, what else do we have? Okay, this one. Okay, we kind of already did this. Okay? It's asking what is the reaction moment MR at the wall? Okay? Well, if we look at the external equilibrium here, we just look at this, right? And we just look at the sum of the moments. And we're going to say in the z direction, and it's important to say where, let's say at the left side. Okay. Then at this location, we have MR, which is positive, okay, assuming that z is coming out of the board. Okay. So MR is positive, and there's no, FR is not contributing any moment there because it's at that location, right? So FR does nothing, but P and L, right, they're acting, and that's going to be a positive or negative. We did this already, right? It's positive or negative. Yeah?
Negative.
Yeah, it's negative, right? So then, just like that. Okay, so then we solve for MR. Here, this one's a little bit trickier, okay? Because we want to figure out what the internal bending moment is. All right, so what we're saying is that we have a beam that now has a length of 1.2 meters, and yours may be a little bit different. And we're not going halfway, we're going to x equals 0.5 meters. Okay? So there are multiple ways to do this, but one way, which is not bad, is to simply look at, they say they want the internal bending moment. Look, we already calculated it out. It's m is equal to p times quantity x minus L. So plug in p, plug in x, plug in L, and that will tell you what the internal bending moment is. Okay? And I think that's it. I think that's pretty much all the homework for tonight. If you have any questions, we can discuss them at the beginning tomorrow. Okay? But I hope you have a nice afternoon. All right. Thank you. Sure.